Hey guys, I'm Raul. Yeah, so I'm from machine learning at Berkeley. We are a research and consulting group consisting of graduate and undergraduate students. Essentially, think of us as one giant AI ML talent pool at Berkeley. And like RobotX Space, we seek to really foster the ML community at Berkeley and get as many minds involved in AI and ML, since it's such a interdisciplinary field that it benefits from as many unique perspectives as possible. So yeah, talk to us after if you'd like to learn more about, I don't know, how you guys can work with machine learning at Berkeley, work with some of our researchers, work with some of our consultants. Yeah, and without further ado, today I'll be presenting on secure deep learning. As we know, deep learning is a very, it's a growing field, you could say. It's getting some popularity. And with that being said, we can't put the cart before the horse. We can't just go willy-nilly and be implementing everything, especially when these autonomous systems have the applications that we can see for these autonomous systems have so much impact on our daily life. So before I begin though, I just want to clarify what I mean by secure deep learning. So in the intersection of security and deep so I also work with Professor Dawn Tong. She's kind of involved in both the security and deep learning field. So in the intersection of these two fields, there are two applications that you can create. There is using deep learning as a security layer, and there's also basically just adding security to your deep learning models. So obviously adding security to deep learning models is much more pervasive, and it's basically if you have any deep learning model, you'll need security. So that's why we're going to talk about this today, as opposed to the other topics, since that is it's much more niche. Come talk to me though afterwards if you'd like to learn more about that. It's very interest. It's an area of research that I'm heavily involved in. And then with that, this is today's agenda. So first we're going to go over some deep learning fundamentals. I don't know how many of you attended RobotX Space's Intro to Deep Learning workshop the other day. Other week we're going to be covering some of that stuff as review, so that it also helps with Ted's presentation later. Next, we're going to be talking about implications of deep learning threats. We're going to be talking about the different degrees of threat. And then lastly, we're going to be talking about how are these security threats generated and how to obviously prevent them, or once they've happened, how to deal with them. So firstly, deep learning fundamentals. Let's just get this out of the way. So stepping back, deep nets, or just neural networks in general, are a simplified model of neural processing. What this means is that in your brain you have neurons that are these singular nodes, but acting in unison through just these numerous connections, extremely complicated connections. They are able to, think. And we haven't come up with an equivalent to the brain so far, so they must be doing something pretty revolutionary that we haven't been able to conceive of yet. So that's why it's such a popular field, since it allows us to leverage the innate power behind our brain and thought and put it in a computer. So a lot of the time we think of neural networks as a black box function. You give it some input X, you get some output Y, and these black box functions are defined by 3 parameters. So the first parameter is the network structure, just basically how the nodes link up. What are the arrows in your directed acyclic graph, or in some cases your directed cyclic graph. I will cover cyclic graphs and recurrent neural networks later. And then the next 2 parameters are essentially connection weights. What is the actual how much does this connection influence your end results? And lastly, there are activation functions or hidden layers. The analogy to this in the neuron or in the brain is, I don't know how many of you guys remember your biology, but essentially the neurons will get some impulse response, or they'll get an impulse signal, but they they won't fire anything to the next dendrite. They won't fire anything across the synapse to the next dendrites unless you hit some activation threshold, and then it sends off its entire signal at once. So activation functions are the computer analogy to this. Instead of having some actual physical gap that our neuron signals need enough energy to cross, we instead input some mathematical function that is nonlinear in some way. And what I mean by nonlinear is that you just can't form them with a linear combination. You actually need to throw a mathematical formula on it. So those are the three parameters of a neural network. And putting them all together, it looks something kind of like this. You have some input X. That looked way better on my laptop. You have some input X, and it just flows to the graph. I'll be talking about computation graphs later, but it flows to the graph, and you get some output. So before we continue, I want to talk about how we define X. So X wasn't one of our three neural network parameters. It's something that just lives out in the real world. It's our data, and the key difference between deep learning and other forms of machine learning is the fact that neural networks are highly data-driven models. So this is something that I tell a lot of my students in my data science class. The key difference between a data science expert and a machine learning expert is a machine learning expert won't necessarily do well on a data science problem. In data science, the reason data scientists are so valuable is they have to accrue years of experience on how to ground data in real world problems. For example, in the most classic data science data set, the Titanic data set, the top results are found or achieved by taking the names of the passengers and performing ethnographic classification on the names in order to achieve the best results. The logic behind this is that Eastern Europeans or people of other nationalities might not necessarily, have had the money to afford top class tickets on the Titanic. That is something that's not in the data. That is something we would not have been able to find with neural networks. That is something that only years of experience as a data scientist could have yielded. So with that being said, deep nets differ in that you don't necessarily need this experience. You just need a lot of data. And yeah, you don't need any a priori context about the data. You don't need to know how it works in the real world. Just more data equals more results. And there are theories. There's theory on how much data you need in order to achieve X amount of accuracy increase. So continuing with this, so neural networks can actually, in theory, model any differentiable function. So any data set, almost any data set we can think of. So given enough parameters and given the appropriate setup of activation functions, or in theory infinite activation functions, it can model any data set. And this is extremely revolutionary since you don't have to sit there and think about how to analyze a problem. Just give it data, and after hours and hours of agonizing training, they'll figure it out. So yeah. And also this differentiable part, we'll come back to it, but it's important. So that being said, what are some of the implications of deep learning security threats, and what do we need to look out for? Or why do we need to look out for it? So recapping from the previous section, neural networks are highly data-driven models. As you add more data, they do better, and increased quality of data also should yield better results. So the data sets then become as valuable as the neural network architecture. People will spend millions of dollars on funding, just going out there and collecting data. One of the more ridiculous stories I've heard is there's a startup in London that has done nothing except make babies cry, make dogs bark, and break windows with millions of dollars of funding in order to classify different types of 911 emergencies, essentially. So in the last 10 years or so, with there's this thing called the AI winter, which was before this burst of big data, this mentality that data is sexy now. And there was also a huge amount of compute power increase like since the 90s, which is when neural networks were first conceived of, when they were first like, when people got really, really excited about neural networks. So with this emergence of big data, we can leverage copious amounts of data in order to train these like deep neural networks. So we now have both compute power and we also have the data that's necessary to train deep nets. So putting these two together, that's why we've experienced this like, it's not significant, and also keep in mind this is like 2013 right here when like the deep net like boom started. So it's probably like a little more over here now, the popularity of deep learning, but essentially you can see that as like compute power went up and as available data went up, everything kind of just follows suit. So yeah, so thanks to big data and thanks to increased compute power, we can now train extremely powerful neural networks. So continuing this and talking about the valuableness of data, let's consider like self-driving cars. They're super hot, tons and tons and tons of ad dollars spent, tons of research dollars spent, and tons of money spent on collecting data, driving these autonomous, or paying people to drive cars and then collecting data. So to preface this, in China there are only 5 companies that have a license to map roads or videotape roads, I guess. So given like the expanse of China, like how big it is, like how the many different scenarios, the many different types of data that you can collect, having access to training data from China is a valuable resource. However, there are only 5 companies that can, 5 companies that can actually like get access to this data. One of these companies is Didi, and then the other companies, even though they're very big, they unfortunately do not have the funds in China to get that data. And so Didi has invested millions of dollars getting like high quality maps from high quality maps and high quality 3D mapping from Chinese roads. So this obviously like affords them a distinct advantage since they're able to see now many more situations for their self-driving cars, and just we just can't compete with that. Like if say Google wanted to launch a self-driving car in China, they'd already be shot in the foot by this fact that they don't have the data, that they don't have access to the data that Didi like has a permit for and spent millions of dollars for. So Chinese driving data is needed. How do we get this driving data? So it turns out neural networks are very easy to fool, and since they're data-driven models, since they were able to tease these patterns, tease these functions out of the data, essentially all your valuable data is encoded within the neural network. Right? You spend hours of training on this data, performing gradient descent. I'm hoping everyone's like a little familiar with gradient descent, but you spent like hours performing optimization on this data. So now your data is actually baked into the model itself, whether you like it or not. And like considering like how fast people are to release like, oh, this is a new level of Google Photos, this works really well, come use our app. If it wasn't for the fact that Google was publicly releasing these data sets, I'd say that that was a complete suicide move, since they like just now basically given out their entire data set. So data is a valuable commodity, and the data is baked into the neural network itself that you're giving users access to, or in some cases you're giving users access to. So going back to this f equals x, f of x equals y function, by say supplying your own driving x, so you're literally sitting in a car, a DD car, and you're just driving around collecting, memorizing how you're driving, and just seeing like the output that DD's autonomous driving network outputs, you can essentially steal all their valuable Chinese driving data just by sitting in the car and just sitting there long enough and letting DD do its work for you. So that's not great. So how do we fix that? I forgot about this. But yeah, so by sitting in this car and getting all the output Y's from input X's that you're feeding DD's deep learning system, you can essentially reverse engineer their entire neural model And in doing so, by reverse engineering their deep net, you end up also reverse engineering all the data that they spent money collecting. So, like I said, large-scale neural IP theft is already underway in several deep learning applications. So a few years ago, Amazon had their product recommendation, the deep net completely reverse engineered and ripped off. So this is something that's already happening, and why we need security in deep learning. So yes, these can acquire expensive resources for free, and they can essentially produce comparable services without having spent the funding on data collection. They just need basically enough access to your API, and they can essentially steal all your IP. Now, this poses some dangers for users and clients. Since neural networks are so data-driven, and they essentially just give you some output Y, given an output an input X, you can algorithmically fool them to output a certain Y, right? A certain output that you desired, or in maybe that you don't desire, in the case that you want them to output incorrect results. So let's consider this case. Obviously, Didi would probably secure the controls to their steering wheel and everything. And let's just assume that you have access only to their computer vision cameras, only what the camera is seeing. Let's also further assume that you don't just replace the video feed. I'll explain what I mean by that in a second. So let's say this is what you're seeing. This is what your car is seeing. Obviously, you don't want to drive into that wall, but someone can come around, an attacker, a third party, and even though the car knows it should stop, they can trick the car's video feed into thinking that they have that the output Y should rely on the fact that there's a problem here, even though there isn't. So they can force your neural network to keep driving forward by, say, feeding it something that makes it think it's seeing, a tunnel. And also, if you had access to their driving feed, you can just replace the video. We'll be talking about other methods that don't require you to just completely replace the video. Since that sounds like a normal security threat, that's not necessarily a deep learning security threat. That's more like an implementation security threat. So yeah, so that will unfortunately happen. You're going to crash, which was not the intended goal. It's just what the neural network thought it should do, given the input data that I'm approaching the tunnel. So if attackers are able to reverse your neural IP, first of all, that sucks since you spent tons of money acquiring it. Second of all, it's extremely dangerous for your users since if this deep net is trying to automate some sort of key life support process, or in this case, driving, which isn't life support but can have catastrophic results, or it's trying to do something like using deep learning as some sort of authentication mechanism, maybe using deep learning as a facial recognition kind of password thing. Essentially, they can keep you out of your facial password protected system. They can make your car crash, and if you're on some crucial life support system, they can cause the life support system to malfunction. So basically now, given that we know the threats or what can happen, I know there's a lot of this sounds very catastrophic, but there are tons of ways actually to defend against them proactively and retroactively, how to defend against them before the fact, and also how to defend against them once your IP has already been stolen. So let me talk about first the degrees of attack. And by attack, I mean not stealing your IP. I mean once you have your IP, how do I, make it mispredict? How do I make it have this erroneous result? So this is a graph taken from Nicholas Paperno's paper, Limitations of Deep Learning in Adversarial Settings. It's a pretty seminal work for the area of security and deep learning, or especially the part about these malicious attacks. It's an extremely seminal piece of work. So essentially what this graph is delineating is, it's basically saying, given some amount of given some amount of knowledge, and given some increasing complexity of the attack that you want to launch, it's basically just saying, nicely formulating the, or telling us how difficult that attack would be to create. So first, let's talk about the x-axis, the increasing complexity axis. So these are the goals. This is what your system wants, or this is what the attacker wants the neural network to do. So there's four types of attack. There's confidence reduction. Not too bad, not the worst thing. If you say reduce the confidence of a Tesla car, it'll just tell you, I don't know what I'm doing, please take over. Not the worst thing in the world. The other three are misclassification, targeting misclassification, and source targeting misclassification. So confidence reduction, not the worst thing in the world. It just basically reduces class certainty. So if you were 100% sure that you were supposed to do something, now you might be 80% sure you're supposed to do something. Misclassification, it's not the hardest attack to muster. However, it's possibly the most dangerous one. So this, by misclassification, I mean literally just give me any result except the correct result. So this is a little bit easier to an attack to launch than the other ones. So firstly, this can mean that the attacker might not necessarily have that good grasp of the model, and also it might just mean the attacker doesn't care. He just wants to commit chaos and disorder, which is terrible in these crucial systems. So yeah, so that misclassification is basically just saying, give me any result except the correct one. Then there's targeting misclassification, which will basically force your system to always output a specific result. This can be pretty easy to implement. Basically gather one sample X per desired Y, and then whenever you want a certain Y, and you basically just feed the neural network the sample that you know will cause it to give you that Y. Source target misclassification is a little bit difficult. It's a little harder. But basically it means given a specific input, give me specific output. It's essentially, given that the output should be a specific result, give me a different output. This is essentially just introducing some sort of confusion map into the system. But it's very powerful because this means the attacker has complete control over all behavior of your system. Next, I'm going to be talking about the resources that you need to launch these attacks. So over here, having this resource means it's the most feasible to launch these types of attacks, and down here at the bottom, it means it's the hardest to launch these kinds of attacks. So the first one is FTC, which means that the attacker has access to your architecture, your function F. It also has access, and by function F, I meant basically the three parameterizations of the neural network. They have access to your weights, your connections, and your structure. T is your training data, so they have access also to all the X's that you had to train your model. And lastly, C is the cost function, so they know 100% how you made your model. Yeah, if they're able to get this, they're probably on the inside already. And yeah, if they have access to this, they can basically do whatever they want. So hopefully good security measures are in place such that this doesn't happen. So yeah. Next is just F and P. This is it's essentially the same thing, because given enough deep learning experience, you can kind of figure out what cost function to use given a certain data set and given a certain architecture. So this is almost at the same level of theft as the previous one. Lastly, you just have some training data T. Since training data is so valuable, and there's basically only so many model architectures you can try for some problems, yeah, then you just pick like one of the state-of-the-art methods for this sort of problem. Let's say you're doing text classification, you just go get an off-the-shelf implementation of Google's Google's sequence-to-sequence model or Google's Google's show and tell model or something like that. And essentially, since you have the training data, which is so valuable, and you hopefully have tons of it, you can train a very equivalent model that gives you almost identical results. Lastly, so these ones are the most, so this one is actually the most likely case. So in Oracle, basically, it's kind of like a chosen plaintext attack. Given that I have some input X, what is the output Y for it? So this is essentially just like you giving your user access to your API and then being able to query it, say, give me this like cat picture, output some Y cat classification or something like that. So that's the most frequently used, that's the most frequent kind of attack. And it's powerful because it allows you to get results that would not necessarily have been in training data or something like that. It lets you get, so this last sample is, this last one is just samples X and Y. This is very similar to the previous one, except the previous one you're able to get even more data since you can supply your own data and further augment the data set that this neural network had to train on. So those are the 5 types of attacks, 4 types of attacks and 5 levels of knowledge needed to perpetrate those attacks. Now, in summary, basically given varying degrees of access to IP, a third party can either reverse engineer or reverse engineer an equivalent or better model, and it basically piggybacks off of all your money that you spent training these models and acquiring data to train these models. No more mic. The other threats are basically commanding the output of a neural network, which isn't necessarily as much a monetary risk, but poses risks for your users. So now I'm going to talk about how these attacks are generated. So this goes back to that Nicholas Paperno paper I was talking about called Limitations of Deep Learning in Adversarial Settings. If you're interested in deep learning, highly recommend checking it out. So in neural network training, you have some cost function C, and you basically have a neural network that, given some input X, predicts an output Y, and that output Y, in theory, you want to minimize this cost function C. And the way you do this in practice is by using gradient descent to train your neural network. So this algorithm leverages chain rule to optimize weights. So that's just, it's just basically, it's nothing special, it's just effectively just a more efficient way to compute gradients than computing every single gradient all at once. You'd basically be doing a bunch of math all over again. But this chain rule computation method stops this chain rule computation just before the input layer at this set of weights. So it only optimizes weights. It doesn't optimize these samples X. So it doesn't, thank you. It doesn't optimize these samples X. So consider basically an input of all zeros for, let's say, n dimensions. And we perform this backpropagation. This chain rule backpropagation all the way to the input layer. So now we find some delta cost function given delta X. Also, if this is getting a little bit too technical and you want me to explain something more, just shout out. So this gradient computation right here, this partial derivative, essentially allows us to find an optimal X to minimize C. I know this doesn't necessarily make sense, just consider this as a thought experiment, since you wouldn't only be finding an optimal X, you'd be finding optimal weights, you'd be given the X. But now instead of minimizing, let's reverse. Let's try to maximize C instead of minimize. We want to find an optimal X to maximize C and essentially make our neural network as wrong as possible. This is kind of the idea of this classification I was talking about before. The actual implementation of it is different. This is meant to be merely a thought experiment, but given the way that we compute backpropagation and given the fact that we can now find an optimal X to make our neural network as wrong as possible, we now essentially have the key ingredients that we need in order to mess with the neural network, I guess is the way to say. So instead though, like I said, that was mainly a thought experiment. You wouldn't want to find the maximal X that makes it as wrong as possible, because that would essentially just give you infinity as the resulting X. So in practice, what we want to do is we want to find the smallest delta X to add to our X that makes our function, our neural network, output a Y. So we still want this optimal X to be similar to our original input, but we want it to be ever so slightly different that it gives us the wrong answer. So I won't get into the math of this. There's a nice proof I linked, and essentially we do this with the sign gradient. There's other methods to do this, and they rely on Jacobians. And I also linked the Clever Hans library, which is, if you do development in deep learning, I'd highly recommend checking that out, as it makes creating these adversarial attacks very simple, and it really helps you benchmark how well your deep learning system does against adversarial attacks. So this is kind of what I'm talking about. So let's say we can clearly tell us that that's a panda, right? But now we add some very small random noise, and we trick our neural network. And now it thinks it's looking at a given, and it's very sure that it's looking at a given, even though we as humans can clearly tell that that is not a given. So that's essentially the goal of these adversarial networks, or these adversarial samples, to trick the neural network, but not to necessarily trick the human. So they're also very hard to detect then, since, I mean, they look the same to us. So obviously, since we can't necessarily detect them well, we want to come up with some method to detect them autonomously, and we'll talk about that later. So here's just another example. These are targeted adversarial samples generated for the MNIST data set. If anyone does machine learning, this is like the classic data set of digit recognition. It's just a bunch of zeros through nines. But yeah, so this is what adversarial samples will look like for a complete input of just zeros. How do I modify the zero input to get me an output? And this is what it looks like. That's what those x's look like after add the delta x. And like, I mean, you can kind of buy that there's 0, 1s, 2s, 3s, 4s, 5s, 6s, 7s, 8s, and 9s. They certainly don't look like any human writing, but the neural network thinks that these are 0s through 9s. Here's an example of source target in this classification. As you can see across the diagonal, nothing happens. But for each of these, it kind of perturbs it with some noise. So I think the best example is this 3 right here. I hope people can see that. But this 3 essentially, after having noise added, it looks to us like a 1. So it's nice that we can analyze this. But the neural network will definitely think it's a 1, and it'll think all those other items in the row are their corresponding thing. See, like, you can kind of buy that this is a 4. Yes? Anyways, so these are just examples of what this looks like in a image sense, in computer vision sense. Also, let it be known that you can't do this for text stuff yet. I won't explain why, but yeah, you can't do adversarial sampling for text systems. So mainly computer vision and signal processing. So now I want to kind of jump into a little demo to illustrate the point. I was going to run this on my laptop, but I created the tutorial on my desktop, which has GPUs, so it takes way too long to run on the laptop. So I'm just going to walk through an already preloaded one. So this is just some install stuff. Also, this notebook will be available after the presentation, so feel free to play around with this tutorial afterwards. More install stuff. Okay, so let's train. So first we just train a convolutional neural network to classify these digits. Very simple task. It's like the bread and butter of every single machine learning class to perform classification on this MNIST data set. So ignoring the error messages, after like very little training, it gets like 97% accuracy. Now, this next cell generates the adversarial samples, and as you can see, the test accuracy is abysmal. This same network that got 97% is now getting 2% on these new samples. And, well, I'll get to the visualization later. This next portion is essentially teaching your network to train itself with these adversarial samples in mind. So this is actually a defensive technique that you can use to help your network defend better against adversarial samples. It's while you're training, be gathering these adversarial samples and also train on these adversarial samples themselves. And don't train them with like the wrong label, train them with the right label that you think it should be. So yeah, so this helps your neural network defend greatly against these attacks, as now it's getting 45% as instead of 2%. Okay, and yeah, I just wanted to now just go quickly over like the adversarial samples that were generated. So here's the original sample, here's a sample that was generated after the first round of training, and here's a sample that was generated after training on both the adversarial samples and the original data set. So even though to us this might look much farther apart from this, actually computationally the result is that this is apparently closer to this than this is to this. So essentially what that means is basically this adversarial sample had to create or this adversarial network now has to create a sample that's much more computationally for it much farther apart from the original sample. So it makes it harder for it to compute adversarial samples that can fool the network. And yeah, I know it doesn't look like that necessarily, but yeah, interpreting neural networks is sometimes hard. Okay, now that we've gone over how these are generated, I want to talk really quickly about how am I doing on time? Okay, yeah, so I want to talk really quickly about 3 methods of defending against adversarial attack, and then go into Q&A session, and hopefully you guys will ask me more questions about those methods of defense. So, common sense, secure your architecture. This is just standard good practice of, this just includes standard good security practices, just making sure, say, people don't have access to your internal logic through like some poorly written JavaScript or something like that. And yeah, make sure your endpoints are secure, everything is nicely password protected, so there's no like, Sony levels of password dumps. And yeah, so limit access to data. So restrict access to the output Y whenever possible. This just goes without, this goes back to the earlier point of if they have an input X from your API that they're supplying, and they have the output Y that the API supplies, they can reverse engineer your neural network given enough usage of your API. And also restrict access to input X. So if it's something that they're not necessarily supplying, but something that says comes from like some database somewhere, yeah, try and encrypt that. Just make sure they don't have access to it. So standard security practice. Now I'm going to talk a little bit about protecting input X. So there's two methods that I like for doing this. There's cryptonets, which are from Microsoft Research, and there's neural cryptography, which is from Google instead. So essentially both of these transform the neural network to work on encrypted data or to basically learn their own encryption structures themselves. So just talking about performance metrics before I talk about like the idea, they basically allow for very high throughput. It doesn't really modify the computation time of your neural network, doesn't introduce any additional lag. Very accurate results, basically the same results you would have gotten if you hadn't had it encrypted. And obviously private predictions, so this protects user data, and also assailants cannot train their own networks without encryption keys. So briefly going over these two methods, essentially cryptonets work by using some public encryption key to encrypt every single aspect of your neural network, so encrypt the weights, encrypt the inputs, and lastly you'll need some decryption key to get the final Y output. So this is important because even if the assailant has all the encryption keys has all the public encryption keys to encrypt the first part of their neural network, they can still make an output prediction Y. However, that output, the output had to have followed the same decryption structure as your original algorithm. Otherwise, it will get similar Y results, but when fed through our neural network, our proprietary neural network, even if they try to generate adversarial samples, the neural network is going to be only approximating that decryption key. It's not going to be the true decryption key, and they won't be able to get, adversarial results through our network. This works in practice by doing some linear approximations to your non-linear neural network, and I've linked the paper there for the more technical savvy people that really want to get into the proofs. Other other methods include neural cryptography, which instead of supplying encryption and decryption keys, the neural networks actually learn the encryption keys themselves. They learn how to protect themselves from attackers. So the way this works is you say train, you have, say, 10 neural networks. You split all the neural networks into 2, giving you 20 effective neural networks. The idea is like the classic Alice and Bob encryption scheme. You want Alice to be able to send messages to Bob, but not, say, Sally, where Sally's in the same classroom, and here a classroom is an analogy for, say, like our 10 neural networks. Okay, so you have basically all these pairs of Alice 1, Bob 1, Alice 2, Bob 2, and you basically just mix them. You just randomly throw them in a mixer, and you make it such that, well, this gets into something called generative adversarial network, but you essentially make it such that unless Alice and Bob are properly aligned, you're not going to be able to get an output all the way through the network. So what this does is, even though they can train, say, like a system that, given an input X, will give you the same output Y as that decryption scheme, after it makes it through the first half of your input, so also at the end, out of this classroom, you'll just choose one pair. So the purpose of this pairing was essentially to just keep mixing them up and only allow the computation to go all the way through when you have the proper alignment. So at the end, you'll choose one pair of Alice and Bob, and these will essentially act as your public and private encryption keys that the neural networks learn. And now when you pass an adversarial sample, say through the first Alice, it's going to give you some output result, but if that output result does not match the format that Bob had, it will not get the correct Y that they were trying to make you have. Obviously, you can still perform misclassification, but it's going to be more luck-based. It's not going to be guaranteed misclassification as we would have had with the other adversarial example where we were getting 2%. So that's neural cryptography and CryptoNuts. I've linked the papers there, and if you guys are interested afterwards, ask questions in Q&A. Next is, this isn't really a reactionary defense. I didn't really know what to call it. So this is watermarking. So this is while you're training the neural network, you essentially teach it to watermark itself. So this has 3 use cases. The first use case is, so many state-of-the-art models are piggybacked off of other models. Remember how I said before you can just go grab Google's state-of-the-art caption generation model off the shelf and just tie it into your neural network, and now you can have some other neural network that performs really well. So what watermarking does is, say if someone uses that neural network as part of their entire neural network, flow, then in their neural network, you're going to be able to find watermarks and certain layers. Next, so this is just basically like, to see who has your model, right? Next, there's this idea of like kind of license keys, where you can essentially make unique watermarks per person. So basically, if they're using, say, your neural network, and then you go and check, you can check if they have your access key or not, and then insert legal battle here. Lastly, you can basically use these watermarks to prevent, that's supposed to be a P. So basically these watermarks can be used such that when the other neural network trains, even though they had no knowledge about what your watermark was, by reverse engineering this f x equals y, their model is going to accidentally pick up the watermark. So now you can just go look to see who has watermarks in their models, and if they do, well, insert legal action here. But yeah, so you can't it's basically used so that someone can take your model and go to town with it and claim it's their own. So lastly is another reactionary defense technique called basically just detecting these adversarial attacks, and it has to do with a technique called generative adversarial networks. And in generative adversarial networks, you essentially have real-world images, and you have a neural network that's trying to generate images or some other type of data. And then afterwards, after the generating process is done, you feed this through a secondary neural network that essentially says, is this from the real data set or is this from the fake data set? These are very hot. There's a joke that there's one new generative adversarial network paper every 2 weeks. It's pretty true. So yes, they're very popular, and we can leverage this idea of training a secondary neural network to detect if things are fake or not by essentially, instead of thinking that there's some neural network generating these images, which there is because there's some gradient computation being performed, won't get into that, but essentially now, instead of feeding a neural network's output into these discriminators, you can feed real-world images and these generated adversarial samples into the discriminator and just detect, was this from my original data set? Is this like a real-world sample, or is this some adversarial sample? Is this some car vision driving input that's been perturbed? So this is essentially a reactionary defense mechanism where if someone is trying to feed bad data through a network, you can say, stop, I know this is messed up, and just not pursue any action on it. So yeah, those are the 3 techniques, and I open the floor to questions.
Will you make the slides available?
Yes, slides will be available sometime in the next 24 hours.
Where?
That I actually don't know. Yeah, they're probably the best bet to ask. Any other questions?
What's the downside of the crypto-based defense?
So the CryptoNet defense or the other defense? So the neural cryptography defense, really none, except for the fact that in training time you have to train 10 different models or however many different models that you want. So it's well, Google just probably has tons of GPUs lying around anyway, so it's probably no sweat for them to train that. CryptoNets have a little bit of a drawback in that they leverage a technique called homomorphic encryption. And essentially homomorphic encryption requires that your operations be linear, and obviously the neural network has these nonlinear activations. So there's some tricks that they do to approximate these nonlinear activations with linear activations. So it does lose a little bit of accuracy, but the end result is still very robust and secure. But like computation-wise, and if you were to deploy like a system that was a neural network that was leveraging these techniques, it wouldn't hamper efficiency at all. And also instead, leveraging an encryption key in the CryptoNet version, you can give the person access to this Alice encryptor neural net in the neural cryptography case. They can use that to encrypt their data and send that off to a server instead. So yeah, there are no real drawbacks computation-wise, just you might take a little bit of an accuracy hit on CryptoNets, and it's just going to take longer to train on the other option. Any other questions?
So how generally recognized is this problem? I mean, how many people are actually working to take precautions against it?
So,
you gave a couple examples.
Yeah, so,
here a couple more
so I don't necessarily know how much is being done in the driving car field. I was just using that as an analogy to illustrate the danger that can happen. I myself have worked for a company called Unify ID, which does basically it leverages your biomarkers, your say gait or something to provide unique identification for a person. So it's extremely relevant there because people don't have access to say your gait, right? In the computer, in the car driving scenario, you can just feed in images that are fake that you have access to, but you don't have access to say someone else's gait. So you have to use this adversarial technique in order to be able to say keep them out of their system or be able to log into their system or something like that. So it's most relevant, I guess, then in scenarios where you don't have access to X, where a certain X that you want to fabricate or perform an adversarial attack for is unique, or the X that maps to some Y is unique. So it's best in that case when you don't know what X is, but you still want it. Or in the car driving sense, like let's say you didn't have access to the video, but you had access to say like impede some noise into some component in the car that messes with the video, and then perform some bad action. You could train a neural network to figure out how much noise you need to impute in order to say, make this car think it's seeing something else and crash into a wall. Yeah. So it's basically used in scenarios where you don't have access to the X and you need to fabricate X.
So who's working on this type of technology? I know you are obviously Google.
I mean, like, I'm guessing Google uses it in some level of their stack. They probably don't say which, or I don't know which levels they use it in. It's mainly theoretical, and I've only worked with it in 2 companies I work for, Unify ID and another company that I'm currently working for called A10 Networks. But yeah, it's essentially like, it's only used in kind of like this personal security or like in A10 Networks case, network security kind of situation. Yeah, it's mainly something that gets implemented when you want this to be secure. Yeah, or it's mainly a research problem is the thing, and the people thinking about it are mainly professors like Professor Song, who advise companies and say this is a key vulnerability. Because also like there probably aren't many people that can perpetrate these sort of attacks. Maybe say if someone made like a universal software, but I could see someone doing very easily from the Cloud Hands library, I think, since it's very intuitive. Unless someone released an API where you don't really need like any knowledge about neural networks to do this, I don't see it becoming too big of a threat, since probably the only people that can launch attacks against Google are probably already Google. So yeah. Any others? Cool. And I think with that, it's time for TED Talk. So, yeah. Thank you.
Awesome.
So great, hope you guys enjoyed that talk by Roll. Now we switch topics a bit to natural language processing. It's a little different, it'll be a bit less into deep learning at first, but we will get there eventually. So natural language processing is a very hot field recently. I myself am also super interested in it because inherently the field of deep learning has really changed these past few years. Before you had all these separate fields, reinforcement learning, computer vision, natural language processing, robotics, but now advances in one field are quickly transferring to other fields. You see fields merge together, overlap, and advances are coming out so fast, it seems every day, that's what it seems like. So anyways, though, this talk today will mainly focus on natural language processing, but towards the end, we'll see some overlap that's going on, what I'm interested in is going on at Berkeley. So to give you a bit of an overview, before I start for myself, my name is Ted. Thanks for the introduction earlier. I'm currently a master's student at UC Berkeley studying electrical engineering and computer science. My main focus research is on machine learning and control systems and robotics, but I'm highly interested in all things deep learning, including natural language processing. So in this talk, this is really fun to put together. I learned some things myself, and hopefully you guys do as well. So to start off with, the question is, what is natural language processing? It's such a buzzword. I'm sure each one of us thinks we know what it is, but really it's pretty simple. It's just artificial intelligence plus linguistics. It's applied not to artificial languages, which are computer programming languages, but to natural languages, what you and I speak with, English, Hindi, Spanish, Mandarin. These are natural languages. And inherently, these make it a more challenging problem because natural languages have less structure than programming languages. And as such, the goal of a human-level agent that can interact and do linguistics tasks with humans is pretty challenging. And the goal overall is to have humans actually be able to understand what computers do, and computers actually understand what humans say and write. So the basic task types in this domain, there are four. The first are syntax and discourse. These are largely from linguistics kind of vocabulary, which is parsing, stemming and such. Oops, that's a repeat, that shouldn't happen. Discourse is more like kind of understanding the actual semantics of the different dialogues. The more important aspects are what we see so often in the news. In semantics, you have all these things. Semantics is actually understanding what is being said, what is actually happening. You see that in machine translation, natural language understanding and generation, QA, all these awesome different things we see on news headlines. Speech too is really hot with all your digital assistants, your Siris, your Alexas, your Google Homes. For some examples, though, this has started not just recently, but actually started long ago. I think the first time I heard of natural language processing was IBM Watson in 2006 when it beat some of the Jeopardy champions. I was like, wow, an agent can actually do all these different things. But natural language processing goes way back. It's actually started in the 1950s with a lot of the World War II kind of analysis. From the 1970s and 80s, there's a lot of statistical methods, but really where everyone really started to think about it in the academic world was in the 1990s with the rise of the internet. With so much more data being put out in written form on the web, natural language processing really took off. So there had to be a lot more methods to be developed that could scale to this kind of level of data and impact. And so a lot more machine learning approaches were used. And then in the 2000s, of course, with the resurgence of deep learning and a lot more very nice data sets, we saw a lot more advances from deep learning, which I'll talk about a bit later. But other tasks that we see very commonly are things like spell check, keyword analysis, sentiment analysis. These are actually pretty easy things from what we know today. And today we've actually moved on to much harder problems. In industry, of course, we see huge opportunities for companies that have taken advantage of advances. We have messenger chatbots, we have digital assistants, we have Google Translate, which has gotten much, much better these past few years. If you have noticed, 10 years ago, you put something to Google Translate, you probably get gibberish out of it. Even though we have all these successes, we have to keep in mind it is still a pretty difficult problem. We actually, have two main reasons that it's difficult. One is we actually don't understand language ourselves. We learn it very intuitively. Children are great at learning language because they pick things up in a very human-like manner, right? You see things, you learn. Monkey see, monkey do. But computers, it's a bit harder. When you say pen, without any context, you know whether it's a physical pen or like a cagey kind of pen. In addition, there's a lot of ambiguity, which you can argue that case was too, but language is very symbolic. People often don't literally mean what we say, and because of this, it's sometimes hard for computer programs to understand what's actually going on. The very cited use case of where NLP fails is sarcasm, right? Jokes, puns, wordplay are things humans love, but unfortunately, computer programs aren't as good at. A very interesting corollary that I like to use to kind of illustrate the challenge of NLP is by comparing it to programming languages. I mentioned earlier that programming languages are very structured, and I'd like to bring your highlight to the red box here. The main differences are in lexicons like vocabulary. In programming languages, you have a very limited number of symbols and tokens that you can use, but in human language, you have virtually unlimited, right? And then in grammatical constructs, programming language has a very fixed constructs. The compilers, the computer programs know exactly how to interpret these programming languages. But human language, you can be so creative. That's why we have so much art with written word. And of course, there's also a lot of ambiguities I mentioned earlier. The single word, a single phrase can mean so many different things, whereas in a programming context, it often can only mean one thing for the program to compile and actually work. So to illustrate ambiguity in kind of humorous context, we see some very funny headlines that if you misinterpret them, they're absolutely ridiculous. Scientists study whales from space. Pope baby steps on gates. These are things that the computer that you didn't train very well read would totally get some nonsensical answers. So speaking of nonsensical answers and disasters, there's something that happened in March last year. There's a company we all may know and love or not love called Microsoft. and they launched something called Microsoft Today. If you remember this, it was huge. They put a chatbot on Twitter, and within 24 hours, internet trolls had converted this innocent little chatbot to a racist asshole. As you can see, it had some very offensive tweets, and many people were very offended. There's many reasons for this I'll touch on later, but what's even funnier, and from my opinion, is that it happened again, from Microsoft again, Microsoft Zoe, December. They had a Facebook chatbot this time that again, got very, very offensive very, very quickly and was also shut down. Do you think Microsoft would learn? So anyways, now that we've kind of given you an overview of where I'm coming from, what I view natural language processing to be, let's go ahead and jump right in. Well, we're going to start with some linguistics backgrounds. It may sound dry, but I promise you it will be pretty painless and pretty fast. Then we'll move on to how we should think about this problem and how natural language processing actually developed with word representation. We'll move on to modern natural language processing, some deep learning, future directions, and then we'll spend a good amount of time on NLP in industry, maybe what many of you are interested in. And finally, we'll wrap up with a quick demo that I worked on last year. So, grammars are the core of linguistics, and linguistics in this sense, I mean the study of language, of natural language from a very academic perspective. Grammars are the rules that define any language, whether it be programming or in this case natural language. We see here that there's different abstract syntax trees that represent where we can kind of put different parts of the sentence into different constructs like nouns or verbs. For linguistics, we have this kind of chart here. It looks complicated, but it's pretty intuitive. You have these different layers, starting with context, meaning, structure, form, and audio. Audio is the very beginning. You have your spoken word, and you've got to interpret that into morphology, which is a big word for just word structure. How are these words actually formed? You move up that abstraction layer, you get structure. How are these words put together into sentences? Finally, you can get meaning from these sentences, and then when you put sentences together, you get context. What do these words and sentences mean in relationship to each other? And from that, you form your entire overall text plot. And in NLP, we think about the problem in a similar way. You start with sound, you go to words, sentences, paragraphs, reasoning, your understanding of actually what's going on semantically. You do something interesting, and then if you want to generate text back out, you go the other way. So each step of this kind of diagram, is active research. There's nothing right here in this diagram that I can say that has been completely solved. There's much improvement in almost all aspects of this diagram that can be done. So promise is painless. As promised, we're moving on now. Now that you know what linguistics, what grammar really means in terms of a natural language, we can start thinking about how we put that into the computer domain. One thing is that natural language is, in many forms, whether written, spoken, or whatever, but computers need a way to understand that. And here in the slide, I think vectors is a pretty intuitive way. I'm not sure how familiar everyone is with math, but vectors, it's magnitude and direction. And you can put it into some kind of mathematical space. And if the idea is that if you can have words represented symbolically as these constructs called vectors, you can do cool stuff with them. You can actually have vector operations to figure out the relationship between words. And in this sense, you've taken something that's very abstract, spoken word, audio, reading, into something that computers can understand. Numbers, math, binary, zeros and ones, encoding it. So in that sense, we get what is called a word vector. However, the space is very large. In the English language, there are 13 million tokens. Tokens are, you can think of them as kind of like words, but words can sometimes be broken up into unique tokens. But many of these are similar words: cat, feline, man, woman, etc. So the idea is that maybe we can take these words and just directly map them into vectors. Each word gets their own unique vector. Everyone's equal. So this is called one-hot encoding with one-hot vectors. So in this sense, we just have, let's just say, and we have 1D, 2D, 3D, let's have in this case, 13 million D, right? The number of words, tokens in our corpus, that's how high dimension our space will be. And we see here that, we encode each word as just a 1 in its own dimension and zeros everywhere else. So each word gets their very own unique representation. This is interesting because each word is orthogonal. They're perpendicular to each other. So when you multiply them, for example, you don't really get anything, you get 0. You can't really tell the similarity between words because they're all different. So the idea is that instead of giving each word its own vector, you can somehow group them. You can keep their relationships, keep some information about how they're similar or different using some kind of different construct. And so I think here is something called dimensionality reduction, which is pretty huge in machine learning. We're working with such big, huge data sets that often you need to reduce the dimensions to something that's more manageable that you can actually learn from. In this case, it's good because you get a smaller space, but you also keep more meaning about how they're related. So this is something called singular value decomposition from linear algebra. I'm not going to go too deep into the technical details here, but the idea is that it's something called a rank K approximation of a matrix X. You'll see how this is useful. Essentially, you have X, one matrix before, and now it's turned into 3 matrices multiplied with each other. At UC Berkeley, in all of our machine learning classes, this is something that's hammered into you because it forms a bulk of pre-deep learning material, and it's pretty crucial to understanding at a deep level what's actually going on in neural networks. So anyways, the idea is that to reconstruct your matrix on the left completely, you can do this U times S times V. However, the idea is that not everything in U, S, and V are relevant or meaningful. So we actually can drop off a lot of it and only leave K number. So you see the orange segments are what we want to keep. I claim that if you take the orange parts and you multiply them together, you'll get something A sub K that's pretty close to A. You've kind of recreated an approximation of A and using way less information. You can see now where I'm heading with this because we can use that kind of method and really go from a huge space that we had before, 13 million tokens, into something much smaller. So here the question is, what is the matrix on the left? What do we put there? Great, we can make it more simple, but what is it? In this case, introducing something called a window-based co-occurrence matrix. So we're simply just going to count how often words occur in a window around each other inside your document. So, in this example, you can read it. I enjoy flying. I like NLP. I like deep learning. We see that like follows I 2 times. Enjoy follows I 1 time, etc. And you put it in this matrix. So I claim that if we can take this matrix here, plug it into what we had before, and then we do this kind of dimensionality reduction, we can still maintain all the relationships we see in this matrix, but by representing it in a much smaller space, they're giving each word here their own vector. So this is kind of a toy example, but there's many other ways, things you can use for X. I'm not going to mention it now because there's a lot of choices, but window-based co-occurrence matrices are a pretty good choice. So we apply SVD, great, now what do we have? Now we have a k-dimensional, k is an arbitrary number that we chose before, hopefully it's much smaller than 13 million, representation of every word in our vocabulary. Now hopefully, because we can reconstruct our co-occurrence matrix, we claim that all the knowledge that this document can give me, I've represented it in a pretty low-dimensional way. Great, now we can get some kind of understanding, what's next? The issue is that SVD is imperfect. It's far from perfect, actually. You can think that our co-occurrence matrix is actually now very high-dimensional. If you have each word and you map it to every other word to see if they're related, 0, 1, 2, get a count of that, this is high-dimensional. That's what we were trying to avoid. Even though you're not at 13 million anymore, maybe you're at you're still at a very high number that's not really feasible. And in addition, this SVD operation that I showed you is very computationally expensive. And it's constantly changing based as your corpus changes. So what's wrong with this? What can we do better? It's when we get iteration-based methods. If you can think that SVD is kind of done in one step, you're spending so much computational resources on this one step, these matrix operations, why don't we just do a little bit of work at every single time step? That's exactly what iteration-based methods are. So as before, we tried to use word vectors and word embeddings. We wanted to find similarity. We wanted to maintain structured information, but doing it in a lower dimensional way. In iteration, we instead want to do that learns one iteration at a time and also encodes probability of words given its context. If this doesn't make sense, hopefully the examples will in the next few slides. So we'll start with some basic language models and then go to the more advanced word-to-vec. Word-to-vec was a monumental advance in, NLP. And this will kind of set this path for how we get from here, where we are now, to word-to-vec. Basic language models, maybe you've heard of bag of words. This is literally you just take a sentence and you forget all sense of structure, which words came before. You just throw them all in a bag together. So you just count the number of frequencies. The issue is that this is still pretty high dimensional and you lose order and relation. These temporal relationships are very important actually in NLP. So maybe we want to keep those. Another option perhaps is something called term frequency inverse document frequency, TF-IDF. And this also adds in the factor of how important a word is. In addition to counting the number of times words have shown up in your document, it also counts, this word in documents compared to all other documents. So even though words like the, of, a might occur a lot, they're not important because they occur in every other document. However, if you have a high number of, a certain term in your document, like aardvark, but not many other documents have aardvark. So you might think that because this document has, so many counts of aardvark, it's important for this document. And that turns out that TF-IDF does a pretty good job of that. However, in both of these cases, we've kind of thrown out word order and the meaning and relationships between words. How can we keep that? So the idea is that maybe we assign a probability not to a single word. What's the probability of this word being in my sentence? Instead, we try to do sequences of tokens. So we say, the dog wagged his tail versus pufferfish bank ladder. This entire sequence, which is more likely to occur? Probably the first one, right? It's grammatically correct and it makes sense. And so the first way we do this is through a unigram model. So this is assuming that words are independent. So even though, maybe the words like car and BMW occur together a lot, the unigram model doesn't count for that. It assumes that each word occurs independently and has a fixed, likelihood of happening. And just multiply all the words together. So we say the is pretty likely, dog is pretty likely, wag is pretty likely, his is likely, tail is likely. Therefore, the sentence is fairly likely. However, we should keep in mind that word occurrences aren't independent. So we get a bigram or an n-gram model where we actually condition each probability on the previous word. We kind of have a sliding window. So what's the probability of this word given the previous word? And you multiply those together. And some examples to illustrate this is here. So, what if our sentence we're trying to predict is cat in the hat? And in unigram, we just multiply the probability of each word directly together. In bigram, we multiply the condition on the previous word also occurring, and the n-gram, we get an even greater window. So I guess these actually, despite sounding so simple, perform pretty well. And the idea is that simple models trained on a lot of data outperform super high-tuned, personalized, customized models that are performed on very small amounts of data. This is the revolution of data that's taking place that I've kind of been alluding to. When you get a lot more data, simple models work really well, even more than things that scientists have labored over in hand-tuning and fine-tuning. So what if, in this case, we kind of keep track of words that came before? What if we keep track of all other words as well? We get something called continuous bags of words, where we consider parts of the sequence's context and try to predict the center words. So I cover up the word in the middle and say, based on the words that came before and after, what's the likelihood of the word? So in this case, I cover up wag and I say, given that the, dog, his, and tail are my sentence, is wag likely? It's pretty likely, right? So in this way, I have a bit more technical detail on how continuous bags of works works. It's also leveraging SVD that I mentioned earlier. But if you have more questions about the internal workings of this, do let me know after the question session. Skipgrams are kind of like on the other hand of continuous bag of words, where now instead of covering up the center word, we cover up everything else. We only have the center word and we try to predict the words that come around it. So dog wagged his tail, we're given wag, we try to predict the dog and his tail. So, and it's a pretty similar method as the continuous bag of words. This is kind of for clarity in case you're looking through the slides later and you want an algorithm of how these kind of things work. Here's a skipgram algorithm. So, as a recap, let's talk about what we just went over in all these different language models and word vectors and what they actually mean. We first started out in a very naive way, just saying we have so many words, let's put them into vectors so we can, see how these words are related to each other in a mathematical space. We got one hot encoding in vectors where you have 1, 0, 0, 0, 0, 1, etc. and we found that this is still pretty high dimension. We used SVD to lower that dimension and see if we could extract very important patterns from this data. However, these operations are still expensive. So we switched to iteration-based methods that are much more efficient. In this sense, however, we use bag of words, TF-IDF. There's no context though, and that's a big issue because languages we know has a lot of context. So we switched over to n-gram models, unigram, bigram, n-gram models. And from this, we saw that these do okay because we have so much data now. And finally, we extended these with continuous bag of words and skipgrams, which are still used in a lot of different applications. So now we've kind of taken a very basic approach. We've been learning the chance that a sequence of words appears together. However, we've been using that solely based on data and just looking at probabilities themselves. Can we learn something beyond just like multiplying probabilities? And the solution is Word2Vec. Came out in 2013. It's been huge at changing everything. Word2Vec does leverage neural networks. We're finally at this stage where we can talk about neural networks. Raul gave a bit of an overview earlier, so I'm not going to cover neural networks. But Word2Vec does is interesting because it actually uses a neural network to learn these distributed representation of words, these words embeddings. So what we looked at earlier with word vectors, one-hot encoding, Word2Vec does a similar operation, but it instead uses a neural network to give it more non-linearity and learn more complex data patterns. And the best part is it doesn't need labeled data like a lot of machine learning algorithms. In this sense, Word2Vec just looks at the data, and their labels are, in a sense, their relations with other words in your data set. And that's the great part. All you need is their position, how often they occur, etc., and all of a sudden you have what this algorithm can treat as, in a sense, quote, labeled data. So even though Word2Vec is a pretty complicated algorithm, is a practical sense you can use packages that do this for you, and the results are really that you are learning the actual semantic relationships between words. You learn how these words relate, and from this you get some pretty cool results. You see that words with similar meanings occur in clusters. If you have these word embeddings, and if you're able to imagine a high-dimensional space with all these words in different spaces on this high-dimensional space, they're actually, you add and subtract, they make sense. This really awesome example is, king minus man plus woman equals queen. And they have this where, you can think of king as a vector, man as a vector, and so on. And this actually makes mathematical sense in the space that they learn. And you can do this with a lot more words as well. This is just a very famous example. In addition, we talked about earlier, this doesn't need labeled data, so Word2Vec is pretty great for unstructured data like text that you see in a lot of sources. And also, this is still being used in many different tasks today in production. So, now that we went over kind of, what's happened from 1950s all the way to just a few years ago with Word2Vec in 2013, we can now move on to what's recently been happening. We have a lot more data now, right? A lot more computational power and a lot more interest in deep learning. Because of this, we're able to leverage a lot of the other advances in different domains, more layers, more neural networks, more computational power, more data. From this, we really focus on different types of data. Text is different from a lot of other training sets because it's so unstructured. It's so abundant, yet so unstructured. We have user data, each company might store in a different way, but you have so much. You have different corpora, which are just like a collection of different types of documents and text. Dictionaries, which are pretty structured, ontologies, and databases. Again, you can run these algorithms straight out of the box on a lot of these sources, but maybe we need something more to kind of unify all of these. Regardless, though, it's pretty interesting to see how unstructured text can produce such amazing results. The data sources, in case, after today you decide, what, I want to play around with NLP, I want to try something on my own or do some tutorials. There's so much out there, right? A lot of people use, scrapers, they crawl, they get things from Twitter, they analyze sentiment, etc. There's, of course, a lot of academic data sets out there that you can use to analyze things. We've talked a lot today about non-deep learning, and now we're mentioning deep learning. How do they actually stack up? Deep learning is, due to its nonlinear nature, tries to encapsulate the recursive nature of natural language. Natural language has so many temporal dependencies amongst each other, amongst different sentences and words, that it's really crucial that we try to leverage these. The methods we talked about earlier, in some sense, can be thought of as very linear, and that's bad when we're thinking about language. So bag of words actually does pretty well on very small data sets, but word to vec absolutely destroys when you feed it a lot and a lot of data. And so we see that a lot of word vector techniques that leverage deep learning perform very well with lots of data. So how do we bring this here actually? Deep learning really attempts to learn not just one level of representation, but multiple. We want computers to understand that human language isn't just simple, it isn't just one layer, you need to actually dig deeper. The different multi-layer structure of neural networks works pretty well for this task. One type of neural network architecture that's shown a lot of promise recently has been the recurrent neural network. Recurrent neural networks are different from the vanilla neural networks, the feed-forward ones that Raul mentioned, in the sense that there's actually cycles now. These graphs are now actually cyclic. You have neurons that are able to kind of keep a sense of memory of internal state on what it saw before and encompass that and incorporate that when it's predicting future tasks and stuff. And in this sense, you're kind of hoping that the neural network can learn the temporal dependency of language that I mentioned earlier. At the bottom, LSTM is long short-term memory. It's just a type of neuron that works for very long inputs. Normal recurrent neural networks work well for normal input, but if you're passing in paragraphs and pages of text, you often run into issues with the neural network not remembering what happened 20 paragraphs ago. And again, at the bottom, these different colored squares, those are just different ways a recurrent network can be architected to output one classification, one to many, many to one, etc. And this will be shown in the next slide. But here is just a really quick visualization of a neuron by Andre Karpathy from Stanford. He has this really awesome blog post on recurrent neural networks. This is actually activations of different neurons inside the neural network. They're looking at these text data, and the green spots is where they get really excited. Something about this data when it's passed to this neuron says, hey, I like what I'm seeing, I'm going to pass through very strong signals. In this case, we see that they're all URLs. So this type of neuron, in this recurrent neural network has learned when it's inside a web page address, which is pretty cool. And there's a lot more examples on his blog post, such as for coding languages, learning when he's when he's indented, when you're between parentheses, etc. He generated LaTeX documents, he generated essays. It's pretty cool. Recurrent networks are very powerful for this kind of task. Where recurrent neural networks have been used to great success in NLP has been sequence to sequence, seq to seq. You'll notice that researchers really like this, something to something, word to vec, seq to seq, pix to pix. And in this sense, RNNs were used. This blue box shows what architecture that I mentioned earlier is actually happening. We have many inputs and we're producing many outputs. In a recurrent neural network, what's happening is we're passing in all our inputs, and at a certain step, we're passing a special symbol that says go, start generating. It will generate, in this case, W, and W is its next input, X is its output, and that's its next input. And like this, it generates something. And in this sense, this kind of structure worked really well in machine translation, English to French, French to English, whatever. Another development has been recursive deep learning, different from recurrent deep learning that I mentioned in the slide before. Recursive deep learning really tries to kind of apply the same weights over and over again to some kind of input. And in this sense, what it's trying to do is fine-tune the weights in the sense that you're really diving deeper into the actual semantic meaning of the text. It's shown to have some promise, but again, this is pretty cutting-edge stuff. We have parsing, paraphrase detection, which kind of phrases are equivalent to each other in meaning, a relation, sentiment analysis. And Raul and I from UC Berkeley were both as part of the Berkeley AI Research Lab, as part of the machine learning at Berkeley. But there's a lot of stuff going on. Berkeley, while NLP isn't a huge focus, there's still significant amounts of work going on. The Berkeley NLP Research Lab, led by Professor Dan Klein, has produced some great work. Even a few years ago, they actually were the ones that had researchers that came up with the prototypes for Google Translate, which is pretty awesome. And in our computer vision lab, which is definitely one of the best in the world, we have a lot of intersections now with NLP, especially in visual question answering. The team recently got first in a visual question answering competition. Visual question answering is when you're shown an image and your computer program has to answer questions like, what color is this cup? Red. How many sheep are in this photo? I'll give you a number. Things like that. So this kind of combines understanding what's going on in the image with generation of actual meaningful text through RNNs. So that's kind of what's cutting edge right now. In the future, there's a lot more stuff that's going to be done, and very excited to see applications and academic theoretical gains. First off, we can actually have bots. Think robotics plus NLP. Both fields are advancing super fast right now, and very soon, if we're able to have bots learn very well, that could essentially, if they're able to pass the Turing test, become like androids or something. We have invisible UI. I'm a huge fan of invisible UI. I personally do have an Amazon Echo, and while it's not great right now, I can truly see if it works well, the promise of it. Where you really have no more keyboards, no more phone screens, no more typing. Something like this is really achievable within the next 10 or 20 years, in my opinion. Smarter search that knows you better than yourself. This is not just human level understanding of human linguistics, as I mentioned earlier, but superhuman level. It knows you better than yourself. It knows what you want faster before you even think that you want it. And of course, instructional deprivation is still a huge problem. We have all these different sources. And if we're able to leverage the differences, not just be hindered by them, that is something that is useful as well in the field of NLP. Finally, I'd like to spend a bit of time talking about NLP in industry and what's going on right now. So, of course, I showed this slide earlier. We have personal assistants, translation, chatbots, financial analysis, but really, there's a lot more that's going to happen too. This was a report done 2 years ago about the NLP market, and it's different trends. Some of these are a bit far-fetched, I think, like in-vehicle speech. That's probably, it wasn't huge last year, probably won't be huge this year, but definitely within the near-term horizon, it's going to happen. How does this happen in industry, though? Beyond the problems that we're solving, what does it look like when you have an NLP system? It's definitely different when you're at a Google or a Facebook and you're serving NLP, machine learning models at scale to millions of users. However, the model that's on the back end is kind of the same. One huge thing you have to do is pre-processing. Because all this data is unstructured, there's a lot you need to do to make it into a format that your model can understand. We have our low-level analysis, semantic analysis, conversion to end products, where all your business intelligence gets extracted out from what you generated. And finally, many of these are structured as an API, so they can not only be used internally for their own products, but externally, such as AWS. At scale, this was an article written by some guys from Cloudera, Databricks, and Airbnb. They are definitely working at a massive scale for natural language processing. For them, they often have to make trade-offs that in academia we don't really think about as much. Systems before algorithms. What this means is that in research labs, researchers will spend night and day toiling on their GPUs to get the best accuracy possible. But in business, faster is always better. So you're able to shave off. You have to make that compromise on what levels of accuracy are you willing to give up in order to achieve lightning fast speeds. Objective functions are really the end goal for your machine learning algorithms. In research, often it's like you're thinking that we want neater objective functions. We want something that's going to be very elegant and work. In industry, however, many influencers have agreed that it's going to be messy. Just go with it, and we need to deploy. We need to scale, and it's all right if it's a bit messy. Everything is of course changing. Papers and new methods are being pumped out from research labs at a rate that I don't think has ever happened in terms of technology, and companies have to adopt to that and adapt. And finally, as I mentioned earlier, there's the optimization trade-off. Some things that will get good accuracy might not be very optimized to run on your backend, so you have to make that trade-off. However, if you're not one of these huge giants that are deploying at a scale of millions of users, maybe you want to test out NLP for your startup or your product. Not as a core value proposition, but maybe as a side kind of feature that will really differentiate you. And in this sense, I think it's important to go through 3 stages. One is to think about what exactly you want to do. What real-world user needs can you actually satisfy with NLP? You can't just throw machine learning and NLP at any kind of problem and expect it to stick. You really need to think about what you're doing. Is it achievable based on what you've seen in the industry and in any research that you've read? And after that, you need to think about an appropriate level and representation. What I mean by this is you have to look at what tasks you're doing and think about the best way to get there. Oftentimes, the most complex models are not always the best. You want to start easy, where it's very cheap to say, hey, this worked, we're done. You don't want to start and spend so many hours on a very complex RNN neural network model and finally find that it works pretty well, but this very simple model that would have taken a tenth of the time to make works just as well. And of course, you have to find data for experiments. Let's see. So our next part is development, where you actually have to look at the frameworks that are available in industry and the tools and really see what to do there. Really popular, of course, frameworks like TensorFlow and Keras. If you're just wanting to do any distributed loads where you're looking at a scale that's beyond just a very simple toy example, you want to use something like Spark. And of course, you want to always be doing experiments to verify if what you're building is valuable and if it's working. Finally, we have production where you're deploying. This, of course, is very CPU, GPU intensive. Many NLP frameworks that we're using in academia labs are not production ready. So oftentimes, you have to take those frameworks and algorithms that you've made on these very easy to develop places and actually make it so that you can deploy it in a way that's fit for your company. So now that you've really tested out the model, you have your idea, it's valuable, it gets pretty good accuracy. Now what? Definitely there are some things you should do. One thing is specifying your performance requirements. Now that we have our model at this accuracy, what performance metrics are we willing to give up on? Do we have to meet any kind of resource demands? And if so, what are they? Then we have the idea that you need to separate your prediction algorithm from your model coefficients. In this case, think of this point A, prediction algorithm, is your software, and point B is your software configuration. As in software, as in SaaS, you want to separate these two. You want to be able to tweak your model coefficients and make it so that you don't have to restructure the entire thing. You want to separate these and make it very easily to swap out, because you'll be doing that if you're working with real data. Finally, you want to benefit automated tests, just as in software. You want to make sure that your models that you developed a year ago, a month ago, are still going to work for the data of tomorrow. So you not only test on back data, you can test on current data. Make sure that if your model is going to fail in the future, that you have an early warning system, and that is through automated tests. Finally, you have back testing and now testing infrastructures. That means that the test I mentioned must be very easy to swap out in your system. So in your infrastructure, you don't want to incur a lot of code debt, because models are often more difficult to change out than other backend systems that you could put on hold. If models are, if you have to retrain your whole model, that's not really easy to say how long that's going to take. You not only have to do that entire step of experimentation, data collection, and exploring again, but you also have to train that and deploy that, and that's very costly. So this last point is challenge then trial model updates. Means that you have to constantly be challenging whether your model is still a fit for your current problem. Oftentimes good enough is okay, but oftentimes good enough actually becomes very bad. And because of that, you want to make sure that if your data is changing to a new data distribution, that what you have is still working. And again, tests will help detect that. So, tips from me, I guess, proper pre-processing is so important. Oftentimes, a lot of data scientists say that your model doesn't matter as much as what kind of data you have and how you feature engineer it and how you process it. If your data is in a very easy to work with format for your model, most models will work pretty well. No matter how hard you tinker your model though, if you don't have good data in the processed format, you're not going to have a good time. Know your domain, of course, investigate, make sure what you're doing is feasible, and of course validate your models. Don't just have an accuracy metric, our mean squared error is so great, we're happy. Instead, also have human eyes to look at qualitatively if what you're doing makes sense. And again, to wrap up, I'll just do a quick demo. Last year, I worked with GitHub as part of a team on programming language identification. This isn't exactly natural language, this is artificial language, it's a programming language, but it's still, we use many techniques from NLP, so I think it's pretty interesting. The idea is that GitHub, whenever you push code, it looks through every single code file and gives you, this is Java, this is Python, this repo is 50% Java, etc. And so what we're doing is making sure that, seeing if we could improve it in any way whatsoever. Right now, GitHub relies a lot on heuristics, hand-coded rules to see, what these different coding languages are, but the machine learning model was really not there. So what we did was we explored different models. We ended up using, this is their existing model, and as you said, if you have the file extension .py.java, it got 80% of files right. But when you took those away, if you only passed in the text without any metadata, it did really, really poorly. That's not a typo, it was only 1.2% accurate. Keep in mind though, there are like over 300 programming languages that they support. And because of that, we really wanted to push it up where if you get onto this 1.2% case, we wanted to build a model that was more robust to getting text only and no metadata. And with that, we actually ended up using a current neural network that I mentioned earlier for feature engineering, feature extraction. Here's a quick video of that actually going to work and generating. You can do that with models. You can make it from a classification model into a generative model pretty easily. And now it's actually generating C code. It doesn't actually compile, doesn't make sense, but it looks like C. There's a lot of grammatical elements of C, the language, that we can see. We have the closed braces, open braces, indentations, semicolons to end. It's pretty real. It looks pretty cool. And we have a similar demo with Python. However, I will not, actually, I'll show it really fast. Because if you're familiar with Python, there's a bit of a syntax difference, but at the same time, our RNN was able to generalize that pretty well. Anyways, yeah, it's not in this model that we created, isn't in production yet, but it might be within the next year or so, next few quarters, so that was pretty exciting. Great. I think that's all I have. Yeah, so anyways, thanks to Jordan Plasky, also in MLab. He gave me instruction for many of these slides, and feel free to reach out to my email anytime with any questions. NLP isn't really my focus, but I had a really fun time preparing this. If you have any questions, yeah, thanks so much.
So what is the current state of research for reinforcement learning for NLP?
Yeah, so reinforcement learning for NLP is actually a pretty new direction. They're applying, also generative adversarial networks for NLP, where you're actually generating new things. Reinforcement learning is actually an approach that machine learning at Berkeley is taking. We're competing in the Amazon Alexa competition, where they chose 10 semifinalist teams across the world to compete for $1 million. Our approach initially used reinforcement learning to kind of teach our agent, Alexa, how to respond in conversational settings. So it's a wide open area of research. Yeah. Hey,
You talked about keyword analysis. So if I had a document and I wanted to do keyword analysis on it, so will NLP be a tool for that?
Yeah, definitely. When we talked a bit earlier about, word vectors, you can also think of word vectors and sentence vectors with word2vec. And in that sense, what Google does is they use PageRank algorithm where they rank different web pages, but they use that on sentence vectors. And from that, given a keyword, you can get the sentences in a document that are the most relevant using existing things already. Word2vec plus PageRank, and you get that.
Yeah, Google has a program called Auto Draw. If you doodle, it will correct and give you a correct picture. It is self-correcting like that. If I'm a lousy programmer, is it possible to using neural network you can correct and do a right programming, something like that?
Yeah, I think it's definitely possible. Right now, it's a bit hard. As you see, the generated code definitely does not compile. It's mainly looking at style as opposed to actual grammar, but that is something that could probably be learned. It probably couldn't generate programs from scratch at the current point in time, but in the future, it's definitely a working direction. Raul, you want to say something?
Yeah, I actually have a friend that works on a company that does, they had the idea of creating like Google and stuff. Essentially, they came up with some machine learning idea that is able to, given your code, is able to tell you like key portions of your code, if you're bugs or something like that. What are like key features? What is it doing? It's called like FOSSA. Still very early stage. But it is very useful.
Any questions? Yeah.
I have a bit different question. It's actually kind of like a task for you.
Sure.
Let's say your provost from his Berkeley is calling to you and asks, you have 6 months to build a non-engineering university course on top of machine learning and NLP, especially using speech to meaning algorithms and tools. Could you describe how will you build this course absolutely without any professor or mentor or instructor course which could actually really teach students this existing knowledge?
Yeah, so I guess the question is using NLP to actually teach students. Okay, that's a bit difficult because it's an even harder task than conversation. Conversation hasn't even been solved yet, right? If it had, we would have passed a Turing test and it would have been big news. But this task, in addition to holding conversations with students, you also want to impart upon them some kind of knowledge. And so, in some sense, this makes the task harder, but in other senses, it might even make it easier because students can forgive you if not everything you say sounds like a human, if it sounds like a robot. When we read textbooks, we don't expect it to sound friendly and like a person. So I think a way to do that would be likely some kind of generative natural language processing technique, like we mentioned with the RNNs, but also to keep in track of personalization. There's been a lot in this field as well. I think Raul was itching to say something again.
Yeah, so actually, something similar was done at Hackathon a few weeks back. Basically, the goal was they want to teach math to students. So they already had the concepts there. They had it in math. They just had to be able to describe the mathematical formulae in like words that made sense to the students. Because like, you know, if you calculate it might have slightly different meaning. So it was very nuanced application of NLP. But they were able to find that, I mean, like, it's essentially a translation of like idea. It's essentially a translation of like the word of the mathematical formula to like natural language. And the key thing that I think was it was able to recognize like you know, if this X is capitalized as opposed to this X, it means something idea. So even though it was like still just a translation thing, it was able to teach the mathematical concepts to blind students. But I know this was like kind of a tangent, but like using a similar sort of setup, I could see it feasible that you were able to like, it might be hard to, you know, like string the concepts together since this gets into like more of the problem like neural network reasoning and something similar to like DQA. But in some way, I think it's possible to spit out the information, and I think it might be feasible to eventually actually teach a neural network to, you know, reason what is the best way to explain this in addition to just explain the concept.
Yeah, I think the task of this is really two parts. One is going from textbook to student, that's like literally teaching them from textbook material exactly what they need to know in a way they can understand. But the other part is a bit harder. So if the student is stuck, how do you personalize the curriculum to what they want to do, what their weaknesses are, what their strengths are. And that's a completely different task. That's no longer NLP. NLP is mainly the medium for which you understand what the student's needs and wants are. The rest, personalization, I guess there's been some study done with neural networks, and not too familiar with that, but I guess what Raul mentioned is definitely the translation aspect, and NLP would play a huge part in that. Any other questions? Yeah.
So recently I've heard about using AI to write code, and that is again potential to replace your software engineers. So I don't know if you have heard of that, but how is it working? Is it an NLP engine that is trying to get the intent and then write code based on the language that it chooses? How does it work?
Yeah, again, I'm not aware of any that work very well right now that you know perfect, but it would definitely rely on some kind of NLP methods, either recurrent neural networks with generative methods, but it would start with the intent, like you said, and then generate based on learned syntax, grammars, and rules, what it does. Raul?
Actually, so this is called an NPI, a neural program interpreter, and it actually doesn't take code at the human level ASCII character text. It takes compiled code, bit stream actually in fact. So it's not even natural language, it's just delving at some language, this artificial bit. And from that, it's able to, like, I don't know, like, simple, I think one of the examples is like, they had a program to rotate a car at 360 degrees since using rapid I guess they're cool. But given just a bit string of like a program and just given enough repetitions of seeing this car being rotated 360, they were essentially able to teach a neural network how to, you know, if you press this button on the car rotating code, you know, give me the actual output, actually compile and run this like button push on this program. So basically, it's using the current neural networks, but it's not natural language. It operates.
Is this the NYU paper?
Yeah, the NYU one is the car rotation. Maybe thinking of a slightly different application, but it's definitely some variant neural program interpreter or neural learning machine. Yeah.
Thank you.
Yeah.
Speculative question. You know, you talked mostly about unsupervised data, which is where most of the work is being done. But to me, it seems like if you want to really master all the subtle differences and meanings that human beings have, somehow at some point you have to build in some supervised, you know, human information system if you're really going to have like a Turing conversation.
Yeah, I guess in this sense, NLP is used, as I mentioned earlier, as kind of like the middleman, right? You go from these conversations and you use an NLP to really understand, unsupervised NLP, like current neural networks, to understand what's going on, but then you run another level of analysis on top of that with traditional neural networks approaches to go from like human language to computer understandable language, and then from that, using label data to match that to intent to do something further. So, yeah.
Okay, so the corollary to that is one thing human beings are very good at is filling in the gaps. You have a conversation with someone, maybe they leave out a word or use the wrong word. In a speech recognizer, maybe they make a misrecognition. But human beings are very good at dealing with that sort of problem. So, is there anything like that that's being looked at?
Yeah, I mean that's very similar to the continuous back and forth we looked at earlier, right? Where you cover up all but the middle word. So it'll take a while, and you try to predict that. There we go. So like dog wags his tail, you take a covered bag, you try to fill it in. So definitely approaches like this, where you use continuous back and forth in conjunction with maybe more complex methods, might do well at that kind of task. Again though, this is pretty hard because there could be many things in that word, right? Wag could be a lot of different things. Maybe not in this case, but in general. So there probably has to be more work done in that area for sure.
Yeah, but maybe the recognizer comes up with the man wagged his tail.
Yeah.
So, but and human beings could, you know, very often deal with that sort of issue.
For humans, it's very obvious, right? The language is intuitive. We know immediately exactly when it's wrong.
Right.
So label data definitely would help with this. Maybe like, I'm not aware of any data sets that have some kind of scale that generate like very incorrect phrases, but in generative approaches, they actually have, a GAN is a generative adversarial network where you generate text, and then the discriminator network will try to predict, is this text generated or from a real human? In this sense, it tries to get better. You have the schooling aspect. Cool?
So this is actually my graduate project that I'm currently working on. And I actually worked on this problem sometime in the last 12 hours. As for the filling in word gap thing, that's actually already being implemented in a lot of NLP systems. So in order to teach it the auxiliary task of being able to fill in gaps and stuff, in your input stream of words, similar to how you drop the middle word in the word effect, or in the bag of words, you just randomly drop words from your conversation, and it has to be able to still have a conversation missing these words. So it has to be able to learn context of how to fill in words, so that's an auxiliary task it learns. And then as for using like, say, label data, or like, you know, it's like, it actually makes sense, like you should be having a conversation with humans to have human interpretable text. So this is actually something I'm working on in the current project, which is involving the intersection of reinforcement learning and NLP. Basically, does this person think this conversation is satisfactory? Does this person think this conversation is bogus or something like that? And using human reward slash input to determine like if, you know, a generated sentence, a generated conversation makes sense. I'm also trying the algorithmic approach of like game analysis. Basically uses stats and gets rid of the human to optimize this process. But yeah, it's a very, using GANs is a very field for, it's very difficult to apply this problem, but it's kind of
Yeah.
So at the moment, do you see any real world applications for natural language generation is it just restricted to natural language understanding and then using some retrieval based predefined responses to respond to the user's query? Do you see any natural language generation? I've seen the accuracy is pretty low based on the training data. Mostly it is the movie dialogue database, but in the real world, conversational commerce or conversational marketing, it's not something that is highly accurate to be used.
Yeah, right now it's not the level where it can be used widely in, I think, the public for mass consumer use, but I do think there's some niches where it can be interesting, where some degree of inaccuracy can be not only tolerated, but maybe even expected. One aspect is perhaps enterprise use. There's a lot of transactions and fluff going on in businesses and communication, and definitely some kind of natural language generation or understanding paired together could cut away a lot of that fluff. I've just been thinking about this lately. Either in IT or corporate or in a lot of these things, these kind of fluff can be maybe taken away by artificial agents. Yeah.
Out of all these NLP methods that you have gone through, right, which one do you think is a good place to start if you have a problem to solve?
I would say, depending on the scale of your problem and how much data you have, if you have very little data, definitely don't do the more fancy stuff. Start with the very simple stuff. Something like even bag of words is a great place to start. If you do have a lot of data, definitely try out using something like Word2Vec with SIBO or something like that. And then if that doesn't work very well, you just go up in complexity. So you always want to start simple and then go more complex.
And what kind of platforms would you recommend?
I personally love Python for anything machine learning related with TensorFlow or Keras. It's, in case you are more familiar with other languages, there's always things like Torch or things like that, if you want to use that. But Python is my go-to. Yeah.
I have a question. I don't know. When we process the NLP, first we use a computer program to parse a text. Is that the parsing part already completely taken care of? The complete parsing tree is already formed? So is that part already done?
Yeah, I think that's part of the pre-processing portion of the task. Pre-processing, we already have many existing things to do that. So generally, pre-processing is not part of the learning algorithm. You don't need a neural network to parse for you, for example. You often have those kind of hand-coded, or you just use existing frameworks to pre-process. Yeah.
So the grammar, everything, all the components, they're already in that parsing tree already. So the parsing is already perfect now.
Oh, like of natural language, parsing it into verbs, nouns, and subjects?
Yeah, right.
That's not perfect yet. It's much better than a lot of other aspects, but I think for a large part, it's not 100% accurate. It's good enough to work with though.
But one thing,
Yeah.
answering the last three questions. As for text processing, parsing, it's very solved in English. It's a weird thing. English is probably the worst in terms of grammar. That's the weirdest grammar. But you can actually use neural networks for parsing in multi-language situations. So what's done a lot in conversations that are constantly switching between Chinese and French or English or something like that, they parse at the character. They use a neural network to analyze text at the character level instead of the word level. Because you can parse the character. That's just, it's essentially just give you the ASCII value, right, of this character. So you're able to use neural networks to learn how to parse words in multiple languages by just looking at characters. So you can use neural networks to do parsing. For the implementation kind of question, TensorFlow is actually really good since the actual TensorFlow library is all compiled in C, and it just has a Python wrapper on top of it. And TensorFlow is really, really flexible in that just by switching out the wrapper, you can still leverage the underlying C++ library, and there's huge communities in other programming languages. So you can use TensorFlow in JavaScript, and it'll just have a wrapper in JavaScript that will be offloading the work to some C++ implementation. You can use TensorFlow in Java, you can use TensorFlow in Lua, other languages. And then for your original, for going back, so using TensorFlow is actually great for implementation since you can integrate it almost anywhere in your network, in your instrumentation stack. So yeah, TensorFlow number one.
TensorFlow is officially supported by Google now, so any kind of updates in the future will now be able to be backward compatible.
It's also very, very stable, like compared to other frameworks. That's one of the key properties of TensorFlow.
If you got Google backing it, it's probably going to be good for the next foreseeable future. So it's a good place to start.
Oh, and then the last question about real-world applications of like text generation. So the problem with text generation currently is it's not able to hold a conversation, but it can actually generate descriptions of like say pictures, an image caption. That's a relatively that's not too difficult of a problem. It's just the problem is it's not able to generate like rich text. Like for any picture with a giraffe and a tree in it, it'll give you the same caption, giraffe standing next to a tree. So it's able to do these menial descriptive tasks, but not necessarily able to hold a conversation. So actually one product that's been launched recently by an Italian AI firm is called Project Forest, and it's essentially for blind people. It's literally just a camera that they wear on their eyes or like can carry around with their phone, and essentially just spits out descriptions of what's happening around the world for them. So they don't necessarily need like guide dog. Like to cross the street, all they do now is hold up their horse, and the horse can tell them when to walk or when to not walk. The horse can tell them what they're seeing in a museum or something. To some general level, it probably won't describe how this is okay. It's a certain thing or something. But yeah, it goes back to this like trade-off of like accuracy versus like implementation of the system. If you want something that's able to just describe what's going on, that's pretty doable actually in the industry right now. But if you want something that's able to hold a conversation with a human and has a point test, that's not, it's like very.
Yeah, most machine learning right now is at an acceptable level. So like if inaccuracies are okay, then a lot of things can be applied directly. But it's only when you have very high bars for quality is when a lot of methods currently have issues. Any questions?
In the neural network, the elements they are like tokens, right? They are words. They are words.
Yeah, your inputs are tokens.
Okay. Can we like put a part of the tree, like a sub-tree of this parse tree, either sub-tree, sub-tree or bigger scope tree into that neural net element. So they could have natural correlation in the neural net element. Would that work better for the?
Yeah, I'm not sure if that's been tried before, but it's definitely interesting so the idea, if I understand correctly, is your parse tree already has extracted some kind of information from these natural languages, and you want to pass that higher level of more refined knowledge into your neural network in the hopes that it's going to perform better, right? Right, yeah.
Because you already have a sub-tree, the sub-tree already has the meaning. They already correlated, the phrases or the.
Yeah, I think it kind of comes out in the wash sometimes, because if your neural network is deep enough, the idea is that the first few layers will extract that meaning automatically. So if you already pass it in directly, maybe you'd save like a layer or two, but you're kind of like front-loading the cost. The parse tree takes time to compute, and the time you save computing that before kind of gets lost with the extra computation you have to do, if that makes sense. At least that's the hypothesis. Yeah.
Are you aware of any ventures or startups at Berkeley that are utilizing deep learning in the healthcare industry?
In the what? Healthcare? Healthcare. I know there's a lot in SF. SF's super hot for healthcare. In the Berkeley area, though, I think there's one for patient care management, but I'm not sure about that. I'm not too involved in the healthcare scene, sorry. Yeah, I think you could probably, definitely approach that field. There's many they ask the same questions over and over again in hospitals. You have to fill out the same forms, and when you ever think of like things that are being repeated and wasted, NLP might be a solution. So, yeah. Any last questions? Awesome, thanks so much.